Can you say hi real quick?
Hi, real quick.
So we have a list of 24 questions that we're gonna ask him. I'm just gonna start by asking him. I just have to speak in the mic. Could you just tell everyone what an astrophysicist is and what you do?
Sure. Thank you for the question. I guess I'll introduce myself and say what I do. My name is Kovi Rose. I'm an astrophysics PhD at the University of Sydney in Australia. So I'm technically talking to you all from the future. As an astrophysicist, you kind of make observations or simulations or theories about how things work in space, and then you use the other elements that I mentioned to confirm those theories, those predictions, those simulations. So for me, I'm an observationalist, which means I mostly work with data from different telescopes that work with different wavelengths, capturing light from all across the universe of different things like stars and planets and distant galaxies. And then I try to understand what I'm looking at, what sort of behavior is causing the light to change, and see if I can match that to theories that we know about how stuff works in space.
I saw you with a question. Yeah, I saw you raise your hand. Okay.
What is a radio telescope?
Awesome. So a radio telescope is a telescope like other telescopes that captures light, except instead of capturing individual photons of light, little particles of light like we are used to seeing with our eyes or with an optical telescope or with binoculars, it's capturing light waves from really low energy light that is much longer in terms of its wavelength. So if you picture a light wave as something that's kind of moving up and down as it goes through space, high energy light waves, things like gamma rays and X-rays, they move up and down really quickly and they have short wavelengths. So, between going up and going down. Radio waves are much longer, the time it takes for the light wave to go up and down as it moves through space. And so radio telescopes are specially designed telescopes to pick up those sorts of waves.
Do you guys have any questions you want to ask? You guys really feel to ask a question. All right, what's your question?
Do you think we'll be able to go to a different planet or fly a planet like this as how we will as Earth?
All right. Do you know if we'll be able to go to another planet soon or something like that, like Mars?
Yeah, that's a really great question. There are folks at NASA and at the European Space Agency and various other space agencies in the world who are working on the Artemis missions. And the idea there is that we're going to land on the moon again and use those technologies to then land on Mars, hopefully in the next few decades. So physically, yes, it's possible. If you're in a spacesuit, you can land on some of these other rocky planets. It's just a matter of getting there. Space is big. The distance to get to stuff is quite large, and it takes a while to get there.
Anyone else have questions?
Is it possible to create an industry via asteroid mining?
Do you think it's possible for there to be an industry of asteroid mining?
I think that it's technically possible. It just becomes kind of an engineering challenge of how can we build the things that can go to the asteroid belts, efficiently mine, and then bring those resources that they mine back to Earth. And for that to be financially viable, obviously there are lots of, or maybe not obviously, I shouldn't say that, but asteroids some of them have a lot of really useful and highly valued metals and minerals that we can use here on Earth. I think, though, the question would be whether it's the smart decision to make necessarily to mine asteroids, and what the implications of doing that would be for, us here on Earth.
What's your favorite part of the job?
That is an awesome question, and one that I don't get enough. The favorite part of what I do is the fact that I get to work on different things all the time. So just today, I was working on one research project that is about a white dwarf star, which is kind of like the leftover dead center of a star like our sun. This is a star that's tens of light years away, and it's doing weird and wacky things as it kind of dances around, orbiting closely with this other star. But at the same time, I was working on a different project today on distant galaxies. There are these things called quasars, which is the centers of distant galaxies that shoot off these really powerful radio waves that we can see from millions of light years away. And so the fact that in the same day, I can be working on two completely different projects, one about stars in our own galaxy and another about supermassive black holes spitting out radio waves in a different galaxy, that is by far and away my favorite part of the job. And it gets even better when I can, discover new things and work on things that are totally different.
Have you discovered like any stars or new things that no one else has discovered yet?
So there was a star that I found a couple of years ago that there are these big survey telescopes that basically look out into space, and they take photos in every direction. And there was this space-based telescope that was doing this, and it was looking for infrared radiation coming from nearby stars. And when you're doing those kind of big surveys, you kind of detect and catalog millions of objects, and most of them don't end up getting followed up. And so that's just kind of like a precursor to say I wasn't the first person to discover this star, but I was the first person to realize that it was interesting. One of these little infrared dots, it turned out, was the coldest star known to give off radio waves. And it's a brown dwarf star. It's technically not a star. It's basically somewhere between a really massive planet and a really small, low-mass star. And this brown dwarf was giving off radio waves as it spun around. And every time it would spin around, it would let off a flash of radio light that we would see. And you can see radio light like that from like normal stars like our sun or more massive stars, but to see it from one like this was the first time that anyone had seen something like that. And this is a star that, our sun has a temperature on the outside of like 6,000 degrees. This star had a temperature of a few hundred degrees. It was basically the same temperature as a pizza oven. So as far as a star goes, having the temperature of a pizza oven or a campfire is pretty cold.
What inspired you to become an astrophysicist?
I was meant to be a lawyer, and I was 1,000% sure I was going to be a lawyer. And that kind of changed when I was 18, 19, and I found this really cool night vision scope that works by amplifying starlight. And I looked up at the sky and I saw that instead of seeing hundreds of stars like I normally would with my eyes, because I was, in the middle of nowhere and there was no light pollution from the nearby cities or bright lights, instead of seeing hundreds of stars, I saw thousands of stars. And I just started reading, and I started listening to space podcasts, and I just fell in love with the idea of space, despite the fact that I was not a math or science person in kind of a strong way. But because I fell so in love with the idea of space and astronomy and discovering the universe, that is what led me to become an astrophysicist.
Why do we have different telescopes to see different wavelengths?
Oh, yeah, that's a really great question. So there are different things in nature that give off different sorts of light. I'm not sure if any of you have seen, maybe in movies or a TV show, that like sometimes folks in the military or like spies will use night vision goggles, or they'll use like infrared or UV goggles to see people in nighttime. So when they're doing that, they're not looking at the normal light, the visible light that's being reflected off them. Instead, they're looking at the thermal light, right? The infrared light that is radiating off them, right? Because even humans, even though we're not a campfire or anything that's, you'd think of as being hot, we have a non-zero temperature, which means that we're giving off thermal light, heat light. But you only see heat light in, let's say, infrared or in ultraviolet wavelengths. And it's the same thing in space. Different stars give off different wavelengths of light. There are some stars that are in a binary and they're pulling material off each other as they orbit around and around one another. And all of this material gets superheated and it gives off X-ray light. So we wouldn't see that if we didn't look at those stars using an X-ray telescope. So different types of telescopes that use different kind of engineering or different physics to capture different parts of the electromagnetic spectrum, different wavelengths, different types of light, that all gives us different bits of information about how things work in the universe.
Does anyone have any questions? Do you have a question? No, I did not understand it. Oh, okay. Is it possible for something to escape a black hole?
So the short answer is no. It gets a bit more complex once you look into the physics of it. But generally speaking, the whole idea of a black hole is that you have a region of space-time that is so warped because of a huge amount of stuff, a huge amount of mass in one place, that even something moving at the speed of light can't move outside of that warped bit of space-time. It's kind of like if you imagine a waterfall, right? And there are these two fish that are swimming towards the waterfall, and one of them swims ahead and he falls down the waterfall. And if he shouts up to his friend who's at the top of the waterfall something, maybe his friend can hear him. But sound, right, would move at a particular speed, the speed of sound. So if he's falling down the waterfall faster than the speed of his shout to his friend at the top would never get to him. And it's the same thing with a black hole, except instead of the speed of sound, it's the speed of light.
Do you have any questions?
What's the opposite of a black hole?
Yeah, I think I could hear that. So yeah, the opposite of a black hole is a white hole. It's a theoretical idea that, as far as I know, we don't have any proof for. So yeah, if you had like negative mass, then maybe you could have a white hole, but that's kind of just like if you take the numbers that we use and the equations and math that we use to describe our universe and flip them upside down, then we would have this other thing, a white hole. But that doesn't necessarily mean that the actual universe works that way.
In how does a telescope work, and how can it be used to see farther into the universe?
So when we think about our eyes are basically taking in light from everything that's in our field of vision. And we're basically taking in a whole bunch of photons, right? These light particles that are coming off whatever sources of light are around us, bouncing off the things that we see, and then, kind of getting captured in our eyes. But then we can only see certain wavelengths that our eyes are able to see, and we're also only able to capture a certain number of photons in the time it takes for our brain to process what we're seeing, right? And so when you think about how a telescope works, it's how can we maximize the number of photons that we can catch, the number of light particles that we can catch, right? So a telescope, in comparison to our eyes, will be able to capture much more of the light and therefore be able to be sensitive to seeing things that are much fainter away. It's kind of like a long exposure on a camera, right? If you take a photo and you tell your phone to just take a normal photo, it captures a certain amount of light. As you click, it closes, and whatever light it's captured in that time is what makes the photo. But if you have your camera on a tripod or on a stationary surface, and you tell it to do a long exposure, and you press the button, it starts capturing light, and it will capture for tens of seconds or a few minutes or whatever, and then it will finish the photo. And so all of the light that it captured in that longer period will give it more information, more photons, more light that it's captured. So telescopes are basically a similar sort of thing. They capture much more light, and they can see deeper into the universe. They can see fainter things and more distant things.
Questions on telescopes?
There's a lot of competing theories for the end of the universe. Which one do you find the most convincing?
Could you repeat the question, please?
I can just say it. Okay, he's coming up.
Come up here if you have a question.
There's a lot of I've read about a lot of competing theories. What? Into the mic? I've read a lot of competing theories of how that universe is going to end, between the heat death and the big crunch and whatever other theories. Which one do you find the most convincing?
So the folks who work on kind of the long-term behavior of the universe over billions of years are people who are cosmologists rather than necessarily astrophysicists. So it's not the work that I focus on. I think that you'd have to ask a cosmologist to get a better answer. But I think that the theory about a big crunch is at least the one that I found the most interesting to read up about. But yeah, it's very interesting to understand how closely these theories depend on our measurements of how the universe is expanding and how it's changing.
Do you have a question?
I hope that answers that question. Yeah.
Are there any recent major developments in your field that you could share with us?
So the thing that I think is the most fantastic part of radio astronomy, working with radio telescopes as opposed to other telescopes, is this idea of connecting smaller telescopes together to build a big telescope. And what I mean by that is normally the resolution, right, of how well we can see distant things in space will be determined by how big of a telescope we have, right? So if you have a small telescope, you can kind of see like either big things or you can see things in a kind of a blurry way. But the problem is, if you try to build bigger and bigger telescopes, you eventually get to a point where like you're building a massive dish that's just going to collapse under its own weight. And so with radio astronomy, there's this really cool technique where you can build a bunch of small telescopes, spread them out over a wide area, and then align the signals, the electronic signals that you're getting from these different small telescopes in such a way that you can digitally recreate a large telescope that's as if it's the size of, you know, that whole area that the small telescopes are spread out on. And you might have seen one example of this recently with the Event Horizon telescope, where they connected a whole bunch of telescopes that are around the Earth into digitally creating one massive telescope that's the size of our planet. And with that, they got incredibly good resolution, so good that they could see a black hole or the ring of light around a black hole in a different galaxy. And I think that this sort of thing is one of the biggest breakthroughs and one of the coolest technologies that exist in my field, in radio astronomy. And we're continuing to do more science by surveying the entire sky using increasingly larger connections of smaller telescopes.
Question?
What has been your favorite project that you've done?
Or worked on?
A project that was really close to my heart was a project that I did on supernovae. So a supernova is a star that explodes at the end of its life. It can either be like a small star that explodes because it has, you know, kind of finished doing its thing and doing nuclear fusion, which is how stars live for billions of years. And, you know, it remains this kind of leftover thing until it might accidentally interact with a star that's orbiting nearby, and then it, you know, will get too much material and it will explode. That's one type of supernova. But the type that I was working on was when you have these massive stars that are like, you know, 10 to 30 times the size of our sun. And when they get to the end of their lives, it's like this violent, chaotic thing where they're like spewing off layers of material into space. And eventually, what's happening in their core, the nuclear fusion that they're doing to sustain themselves, collapses, and the whole star collapses under its own weight. And that's called a core collapse supernova. Not a very creative name, I know. But when this happens, basically, the star implodes and then explodes, and that explosion moves out through space. And radio astronomers and other astronomers pick up the light of the shockwave from that explosion going through space. And every time that shockwave, that explosion hits some stuff, some material, it changes the light that we see. It makes the light increasing brightness or change to a different wavelength. But as I said, before the star loses its, before the star implodes, it's losing a lot of stuff into space and shooting off material. And so as the explosion happens and the explosion front, the shockwave, hits those different layers of material, you can study that material. You can study what happened before the explosion by seeing how the explosion moves out through space over millions of miles as that explosion moves out in space. So that takes a long time to happen for the explosion to get further and further out. And my favorite project that I worked on was something that I started close to 5 years ago and finally finished earlier this year, where I basically found these cases of supernova, these exploding stars that exploded, got really bright, and then faded away into nothing. And then years later, they suddenly got bright again as that shockwave as an explosion hit material that was further away from the star. And it was a really cool long-term project that I had a lot of help on from the people I work with. And yeah, it was a really fun project to work on, and it was really interesting for me.
What are your thoughts about the ocean discovered on Europa, and do you think there's a possibility of life on that moon?
It's a really great question. There's been this tendency for us to look for life in the universe historically, for life as we know it. I'm sure that's an expression that you might have heard before. And so, yeah, being able to find subsurface oceans on moons of Saturn and Jupiter are really great places to look. We definitely need to keep sending probes to go and fly around these icy worlds in our solar system to find if there's any life that looks like life that we know that can survive in liquid water. But some of these oceans, as you might know, are not liquid water, they're liquid methane, they're liquid gases. Well, that's a bit of a contradiction, but they're things that on Earth we would consider to be gases under normal temperatures and pressures. But you can have things like methane or things like it that are in liquid form in space if it's cold enough. And it's possible that life could develop there. And so I think that one of the things that we need to consider is when we look for life in our solar system or elsewhere in our galaxy, are we also looking for life that could be life not as we know it? It could be life that forms in different ways and lives in ways that are totally different to the life that we see here on Earth.
Have you ever detected something unexplained or like evidence of dark matter or anything like that?
So the telescope that I work with, it's this telescope here in Australia that basically scans huge parts of the sky on a regular basis. And the work that I do is to look for things that appear out of nowhere. So in one image of the sky with this telescope, there's nothing, and then suddenly there's something. Or, for months we're seeing some like low-level brightness from this one point, and then suddenly it gets really bright. And all of these things start as unexplained when myself and my colleagues find them. And the cool part of my work is figuring out which of these things are stars, which are supernovae, which are maybe systematic issues with our telescope, or somebody turning a microwave on at the telescope. Unfortunately, there are all sorts of human-made signals that can impact what we see with a radio telescope. And so figuring out what are the interesting things that we're seeing that are known objects and what are the systematic issues is the bulk of the work. But yeah, as you suggested, there are some times that we find things that we can't explain. And there is one project that I've been working on now for about a year and a half, close to 2 years, where I think we have figured out what we're looking at. I can't tell you what it is, but I can tell you that it's not aliens. It's not anything like that, but it's a really special discovery from an astronomical perspective. In terms of dark matter, that's not the sort of thing that I work on. There are some really, really good science being done by people just down the hall from my office who work on dark matter. And I think the study of dark matter is super interesting because how can you detect something that we can't directly see? So there are folks who are working on various indirect detection methods. And yeah, I think that's super cool, but it's not something that I work on.
Has anyone like you've been working with or you detected like life in space?
So I'm assuming that you're not talking about the astronauts on the International Space Station, right? In terms of life in space, there have been some claims that folks have found signals in the chemistry of the atmosphere of Venus, that those chemicals that they found, if they did indeed detect them, would point to there being something on Venus that created those chemicals. Outside of that, as far as I know, there's very little evidence that we've found so far for life in space. But I expect that over the coming years, especially with amazing telescopes like the James Webb Space Telescope, we're going to be finding more and more potentially interesting signs of life in our galaxy.
So, like, has there been any cases where, like, you discovered something, like, pretty far back, but, like, even still today, you really don't know what it was?
Yeah, that's an interesting question. I think that a lot of the time in astronomy, you are left with questions and uncertainties. And I think that a lot of the work that we do is to try to figure out the best, most reasonable answer, or in some cases, answers, plural, that could explain the thing that we're seeing, even if we can't definitively say it has to be this one thing. So yeah, there are these weird objects that myself and some of the people in my research group have been working on recently that are called LPTs, long period transients. A transient is something in space that appears and disappears. And when they say long period, they're talking about something that flashes and disappears on a time scale that's periodic, on something that repeats with a period of several minutes or several hours. And there are these really fast, really short period transients called pulsars, which are basically after a star explodes as a supernova, it leaves behind this really dense thing called a neutron star. And the neutron star, as it spins multiple times per second. And as it spins around, it gives off these really fast bursts of radio light. But the problem is with long period transients, the bursts of light are moving much slower, much too slow for it to be a pulsar. And the bursts are also much too fast for it to be a regular star. There are also these really fast bursts that are unimaginatively called fast radio bursts that are even faster. That's something that appears and disappears in milliseconds. And we think that also comes from neutron stars, from these really dense leftovers after explosions of massive stars. And most of the fast radio bursts that we've discovered come from other galaxies. And so long period transients are these really, really interesting things that we keep finding more and more as our telescopes get better and better, that fall in between the behaviors and the characteristics of pulsars and fast radio bursts and regular stars. And so they kind of have a bit of both. And it's an ongoing mystery that we're trying to figure out exactly what these long period radio transients are.
If you could go to space, like, would you, if you had the chance? And if so, what would you do in space?
So, I get this question a lot. As an astrophysicist and not an astronomer, my chances of going to space are not particularly high, but they're not zero. I mean, I guess the chances these days for any of you to go to space is not zero. If that's something that any of you in the audience are interested in. you should definitely work towards that goal because it is possible. For me, if I got that opportunity, I would probably spend the whole time just staring out the window. I would be looking out at the stars, trying to see what I could see, or I would be looking down back at Earth, because from what I've heard from every astronaut that I've spoken to or read their things that they have written, there is nothing more beautiful than being in space and looking down back at Earth and realizing that everybody that you know or have ever known or heard about or read about, anybody whose YouTube videos you've watched or books you've read, they are all on that little blue dot that you're seeing from space. So I would spend most of my time in space just staring out the window.
What are your thoughts on the Big Bang Theory and what, I guess, was in our universe before that?
Yeah, it's a tricky one because you kind of think the Big Bang was the point at which all of space-time, not just space, but all of space-time started moving outwards from that one singularity, that one single point. And it's kind of not feasible to talk about what happened before the Big Bang, because if you have time starting at zero, well, what's negative time? What does that mean? So the Big Bang as a theory is something that successfully explains so many different things that we see when we look with our telescopes out into the universe. We see, for example, when you look out into space, because things can only move as fast as the speed of light and never faster, right? That means that when you look further out into space, deeper in space, and you're seeing the light that left somewhere earlier, you're actually looking back in time. Doing astronomy in a weird way is kind of like time travel, right? So the deeper you look into space, the further back in the history of our universe you're seeing. And so when astronomers look back as far as we can see, we see to distances that are around 13.8 billion years ago. And at that point, you see the leftover radiation caused just after the Big Bang. That light that's called the cosmic microwave background radiation, that's the light that is left over from that snap of a moment after the universe following the Big Bang cooled down just enough to let the first light escape. And when we see things like that, and you see things like the distribution of galaxies throughout space, all of the evidence that we see points towards the Big Bang as a theory. Obviously, there's still a lot of work to do, and that's where cosmologists come in. But yeah, I think anybody can say in a casual way, like, oh, I have a theory about how something happened. But when we're talking in science about a theory, especially a theory like the Big Bang, it's not just, what some guy believes. It's all of our models and all of our equations and data and evidence point towards this being the way that our universe formed.
What are binary stars and how are they different from our solar system? Or the sun?
Oh, yeah, great question. Yes. Yeah. Folks often talk about where is the nearest star to Earth, and they're expecting me to say Proxima Centauri or Alpha Centauri. But actually, yeah, it would be the sun. So outside of our sun, our solar system, which is a single star, right, with 8 planets that are orbiting around it. Most of these stars that we see in the Milky Way are, on average, actually binary stars, which means that you have 2 stars that are orbiting around each other, right? the way things generally work in space is that gravity pulls things together. And so when you have the formation of stars, which forms from these gas clouds of hydrogen and helium that are pulled together because of gravity, often what you end up with are these things called nebula. And a nebula, like these pretty pictures that you've probably seen in Guardians of the Galaxy or some other Marvel movie, a nebula is this beautiful cloud that's forming stars. And so when stars form together in these little stellar nurseries, you often end up with clusters of stars forming near each other or at the same time. And what will end up happening is that you will have multiple stars that end up living the rest of their lives together in a binary system, in a system with two stars. You can also have trinary systems that have 3 stars, in some cases more. I think on average, most stars that we see in the night sky are actually binaries.
Why is Pluto no longer considered a planet?
This is a fantastic question. The problem with studying the universe, right? The universe, which is this enormous thing that functions on scales that are totally irrelevant to human scales, right? I'm talking about stars that are separated by millions of miles, things that weigh trillions and trillions of pounds. So scientists just have to do their best at finding ways to classify things in space to figure out what the relations are between different things, right? So we say that a planet is something that orbits around a star, and planets can kind of have, these sorts of masses. A moon is something that orbits around a planet, and moons tend to have these sorts of masses. But the problem is that we're trying to fit nature into boxes. We're trying to fit things into categories. And a lot of things in the universe tend to not fit neatly into boxes. A lot of things are more kind of on a spectrum. And so when it comes to Pluto specifically, we have to rely on a definition from one particular group of astronomers. It's a very large group of, and a very old group of astronomers called the International Astronomical Union, the IAU. And they're kind of this large group of astronomers that gets together every year in this general assembly, and they decide on kind of rules and definitions for how things work in space. They follow up research. They choose how, education programs might be funded. And so the IAU had to update their definition of what is a planet, because when you get to the distance from our star, from our sun, that Pluto is at, there are actually a lot of other small, what's called dwarf planets, things that are kind of like really small planets, but maybe too big to be moons, that are also orbiting around the sun at that distance. And so according to their definition, to be a planet, you have to be kind of have like the self-gravity to pull yourself into a ball shape. You have to orbit a star, but you also have to be the only thing orbiting the star at that distance in that path. And so we don't know for sure. In fact, there's evidence to suggest that there are other things that are in that same path that Pluto's orbiting in. So it's not technically by that definition considered a planet. But I think focus on the first half of my answer, which is that it shouldn't matter. It's just about how we have to define things to help us understand things.
How do suns produce heat or energy?
Oh, yeah. This is a great question, and I hinted at it before when I said nuclear fusion, and I kind of threw in that phrase, nuclear fusion, and then I continued on my merry way and didn't actually explain it. So thank you for calling me out on that. I will explain it. The way that things work in space, as I mentioned, is there are not a lot of other forces acting on things. So if you have a cluster of gas, it will cluster together. Or if you have two clusters of gas, let's say hydrogen gas in space, it'll be pulled together because of gravity. And if you have enough stuff that's being pulled together, it will pull in one place because of gravity in a symmetrical way, and it will form this really dense ball of material that's called a protostar. It's like the precursor to a star. And so what happens is that there is so much pressure from the stuff being pulled in together that you can have individual atoms like hydrogen that are fused together, they're forced together. And when you can kind of compress atoms together, you create different atoms, heavier atoms, different chemical elements. And so most stars, like our sun, spend billions of years just fusing hydrogen into helium. So you have gravity pulling everything in, that causes nuclear fusion of hydrogen into helium. And then that nuclear fusion creates so much energy that it creates a force that pushes outwards, and it kind of counters the gravity pulling in. So that nuclear force from the fusion that's caused by gravity is the thing that pushes outwards. It's the thing that creates a lot of the radiation and light and energy that we see from stars.
Do you have any final questions? Or I think.
So one more final question, and then I have one.
Okay.
So you said like how Pluto is a dwarf planet, like about how big is it? Like, is there anything we can like compare it to like just know, like about just how big it is?
So I can't remember the exact size off the top of my head, but there are moons in our solar system that are nearly bigger or around the same size as Pluto. And that's why these things get tricky, right? So you can Google the size of Pluto and at the same time Google the size of, let's say, Europa, which was brought up in one of the previous questions. And when you can compare the sizes, you realize that it's not just about how big it is. That can't define it as a planet. It also has to be defined by, what is its host? What is the thing that it's primarily orbiting around? I hope that answered that question.
Did that answer the question? Yes. Yes, it did. So,
okay, great.
Before I ask my last question, can we all give Mr. Rose what? Were you going to say? No, go ahead. You do it.
No, it's fine.
Okay. So I have a question, and they can wrap up. So you have a whole bunch of kids at different age groups, some who are in high school, taking finals tomorrow. And some of them are trying to think about what they want to be when they grow up. Do you have any advice for any scout here who may want to be an astrophysicist when they kind of move through their high school and into their college careers?
Well, firstly, I just want to say that to anybody who has finals tomorrow, I really appreciate you taking the time to come out tonight, the night before your final, to listen to me blabber on about space. And I wish you the best of luck in your finals. As I mentioned at the start, when somebody asked me why I became an astrophysicist, I fell in love with space and then realized I have to do I have to learn the math. I have to learn the science. I have to build up a scientific tool belt so that I can work on the thing that I love. And that's not a traditional way of, becoming a scientist. But more and more, I notice so many of my friends and my colleagues are people who also had non-traditional paths, right? So it is possible that if you want to become a scientist, if you want to become an astrophysicist, that you should, work hard on math and science. And also, I would say data science, like learning computer programming, is incredibly useful for doing any science these days. It's a lot of the work that I do. But also, I would say that the important thing is to kind of look for the thing that you're passionate in. And if you find something that you're passionate about, a particular field of research or a particular career, following that passion and then learning what are the particular tools that you might need along the way, that would be the best thing that I could recommend. And always, remembering that it's okay to ask questions, and there is none of us know all of the answers, so we all need to rely on help from other people. So yeah, keep asking questions and follow your passions.
So if we could all just say thank you to Mr. Rose for coming out here and teaching us about
Hey, Kovi. Thank you for joining us. And Pluto is the size of Russia. Same surface area. There you go. Thanks for joining us, Kovi.
Thank you all for having me. It was great fun. Enjoy the rest of your night.